welcome everybody to this transatlantic seminar. And it's a great pleasure to have today Lisa Traynor, and she will talk about the geography of immersed Lagrangian fillings of Legendrian submanifolds. And I wish to remind you that questions are really very welcome. So please do not hesitate to send them either via chat, or you can in principle unzoom yourself and ask. So whatever works, but I think it's kind of important to also for the speaker to have feedback. And after an hour of a talk, we will assume to have discussion. Yeah, so ask questions, and we have extra half an hour for this. So please, Lisa, go ahead.
Okay, great, thank you. So, well, I appreciate this opportunity. So yeah, I'm at Bryn Mawr, which is outside Philadelphia. And this is my first Zoominar. So I've been doing a lot of online teaching in the last couple of weeks, but I think I'm set up so I can see the group chat. So again, you're very welcome to ask questions. Okay, so today I'll be talking about a project that was joint work with Samantha Pezzamenti, who finished her PhD at Bryn Mawr a few years ago. A lot of the results that I'll be talking about, some of those results kind of came up in her thesis, and we've been just extending and polishing it. It hasn't quite appeared on the archive. It was going to pretty soon, maybe without the coronavirus it would have appeared, but it should appear soon. So Sam is at Penn State Brandywine. Okay, good. So let me just start. I'm just going to start about talking about this problem, which I call the geography of fillings. So I'm setting this up. I wasn't quite sure who the audience would be. So let's just start even in the smooth world. So this is what I call it's just a topological problem you can look at. So if I start with a knot inside S3, I can try to find smooth filling surfaces. So this is, topologists usually don't call them filling surfaces, but that's coming more from the symplectic world. But what I just mean by a filling surface means like a surface inside the four-ball that has the knot as its boundary. So there are lots of options for this. So for example, if you looked at a trefoil, you could find a genus 1 filling or a genus 2, but you couldn't, and higher, but you could not find a disk filling for that. So usually in the smooth world, something that a lot of topologists look at is that four-ball genus. You just try to find the minimum genus of a surface that bounds the knot. Okay, so the four-ball genus, that's something that has been studied a lot in the smooth world. You can also look at immersed fillings. So I'm always talking about immersed fillings where there's transverse double points. So for example, if I again look at the trefoil, there wasn't a disk filling, but you could find a disk filling with one immersed point, or you could find a genus 1 filling with one immersed point. So often in the smooth world, people have looked at this, what they call the four-ball crossing number, which is just we'll restrict to the genus 0 case and just look at the minimal number of double points in a disk filling of the knot. So this number has been studied. There's a really nice paper by Sterling Owens from a few years ago where they used a lot of Haggard-Flair homology in addition to other techniques, but they were actually able to calculate this four-ball crossing number for all prime knots with 10 or less crossings. So in the beautiful charts at the end of their paper where you can just kind of look up all these numbers, which is very helpful. So in particular, today, and just follow some examples, I'm going to be looking at the M52 knot, Mir52, and the 7-4. So for example, the Mir52 has a disk filling with one double point. 7-4 has a disk filling with two double points, and that's the best that you can do. Okay. So now I'm just going to introduce this geography question. So first just in the smooth world. So if I'm given a knot K inside the S3, you could look at, for me, geography is what's the combination of genus and double points. So today I'm going to be drawing a lot of lattices, and I always draw the genus on the horizontal axis and double points on the vertical axis. Okay, so we're looking at the lattice points here. And I'm just trying to figure out for a fixed knot, which lattice points can be realized. So if you can realize one, you can always kind of move north. You can always go up. It's always possible to fix the genus and increase the number of double points by 1. So a nice way to kind of see this is like as you start to, if you have if you follow the trace of an isotopy of your knot, or a regular homotopy. So if you start to introduce a self-crossing, you can imagine doing a Reidemeister move, a Reidemeister 1 move, and then crossing it through itself. So you can always see that you can increase the double points by 1. Okay. In addition, you can always move to the east. So you can move north, you can move east. In other words, you can fix the number of double points and increase the genus. So here we're just do a handle addition to your surface. And another basic move to realize is that you can always move southeast here. You can eliminate a double point at the cost of increasing the genus. So here is just a surgery. So move the double point and include a handle here. Okay, so let's just look at some examples. And again, using the charts in the Stirling-Owens, you can actually do this for all prime knots with 10 or less crossings. So here's how I'm thinking of like the smooth geography of M52. So again, you're seeing in this chart, the green shading is just for the eye, but what you're seeing is all the lattice points that are in the shaded region can be realized. So in particular, this one it's kind of most interesting right on the edge here. So this is the 4-ball genus is 1, and the 4-ball crossing number is 1 here in this case. And again, then everything, again, you can always move north, you can always move east, you can always move southeast. So everything in this region can be realized. There's also, here's another example that I've been thinking about. 7-4 has caught my attention recently. So 7-4, this is a little more interesting. So there's a lot in those small prime knots where you really kind of have this triangular cutoff. But 7-4 is a little more interesting that you kind of have this kind of chop region here. So again, the 4-ball genus is 1. The minimum number of double points is 2. Okay, so that's the smooth geography question. But you could also do it in higher dimensions. So, so in particular, given a smooth m-dimensional submanifold, you could ask what combinations of Betti numbers and double points can be realized. And again, so here, my submanifold now is living in S2m plus 1. My fillings, I would want to live in B2m plus 1, and the dimensions here accordingly.
Excuse me, there is a question from
Okay.
Claude.
Right, yeah. So can you always replace genus by a pair of double points? And so kind of going back to this, okay, so if I fix the genus, can you go like up 2, or just, in general, you can't always go northwest in some sense. Is that answering your question, Claude, or?
So what is the answer? Can you always do that?
Can you always go like northwest? Like no,
two steps up.
Oh, 2 steps up. Actually, I'm not quite sure.
Okay.
Yeah, I'm not sure. That's a good question. Someone might in this audience might know.
Lisa, you said that you can go always up and you can go northwest once, right?
You can go up, you can go north, you can go east, you can go southeast, so you can go down. So given a double point, you can resolve the double point
Right. Okay,
by increase. Yes, but going the other way, yeah. So in general, from this point here, that's why I tend to draw this little triangle here. That I can, well, I should put like a little arrow. I can always go downward along there.
All right.
But for example, I can't always go upward, and you can see that even for the 7-4. Oh, good. Grisha wrote, naively wouldn't expect it. Yeah, so, okay, so maybe we wouldn't expect that you could always do this 2-step up, but.
Grisha, maybe you comment because I'm not sure.
Yeah, Grisha, do you want to say something?
Comment was that just suppose that we have a genus, right? So genus we can think of a circle, then it would be a boundary of the membrane. And suppose we have a membrane with self-intersection -1, then we replace it with a single point. If it's a membrane with higher self-intersection, say -2, as probably in this case, we would replace it with 2 nodes, but maybe for some more complicated surfaces, we can have membranes of higher self-intersections and so on.
Okay, so Kyle had a question. Smoothly, you can always get to double points. The crossing trees, you can get to an immersed disk. Yeah. Smoothly, yeah, Kyle was just kind of mentioning, and Kyle, you can unmute yourself. Yeah, it's just kind of mentioning that you will always have something on this line here. Yeah, so again, because every knot can be unknotted, there's an unknotting number, so that will tell you that you can get an immersed disk filling of everything. Kyle, did you want to say anything else? Or?
Oh, no, it was just in terms of replacing genus by pairs of double points. I mean, not in like a compression way, but just exactly what you said, that you could, in theory, add tons and tons of double points and eventually get down to, although you're not really replacing the genus by it.
Right. Yeah, so you always know that there's something in the shaded region, there's always going to be something on this line. You know, that's why you're trying to find the minimum of ball crossing number. So.
Okay, thanks.
Good. Good, I like this chat. This is good. Okay, so let me go back to here. Okay, so yeah, so it's interesting even in the knot world where we do have some information. I really don't know what's known about this higher dimensional version. So for example, I mean, there's some restrictions from algebraic topology for embedded fillings. I mean, you have long exact sequence of a triple, you know, the boundary and the surface. But I don't really know if anyone's looked at this question for higher dimensions. If you start to add in, you know, what's the restriction on the topology, the, you know, double points and embedding numbers in this higher dimensional. So if anyone has ever thought about this or has any suggestions of where I could look for some sort of results here, that would be interesting.
But I have a question. So can things of dimension m and dimension 2m+1 be noted? So it's codimension m+1.
Mm-hmm.
Basically, you do not have much knot types, probably, right?
Yeah, probably not much knot types there.
Yeah.
But I'm still, yeah, so, so that much you can kind of say, but I still don't know if, maybe it's, yeah. So for the embedded part, yeah. Good, okay, so that's just kind of the smooth world. So now I'm just going to very generally introduce the Lagrangian geography problem. I'm not going to make this very precise to start, but just to give you a flavor of some of the questions and the results. So now just instead of a smooth knot in S3, I'm just going to say there's a Legendrian knot in a three-dimensional space. And I'm going to find Lagrangian surfaces in a four-dimensional space. And that's kind of the goal. We want to try to find them, embedded or immersed. And the question always from the symplectic world is like, how flexible or rigid are Lagrangian fillings? And in particular, we can ask this in this context by asking, how does the Lagrangian geography compare to the smooth geography? And here, what I'll be talking about, most of what I'm presenting, just the examples, are going to be lower dimension, but the techniques that I'm using apply to higher dimensions. And I also think that's interesting. Okay. So just as a preview, I'm going to make all of this more precise, but here's like a preview of what we will see, is that I'm going to study this problem using the generating family technique. And so we're going to see a lot more rigidity. So here's for an M5 knot. Here's what we were seeing in the smooth world. Again, so in this green, all the lattice points that are in this green region can be realized for a 5-2 knot, M5-2. But in the Lagrangian world, you get sort of this check mark sort of edge. And then it's not all points in here, but there's going to be a mod 2 relationship. So kind of all the kind of odd points in that lattice. And for example, this is for 7-4. Again, those are the main two examples I'm just talking about today. Here's the smooth world again. Again, that kind of interesting corner trapezoid down there. But this is what the Lagrangian world looks like. So a little bit different, still kind of this weird chunk out of it, but that's what we will see. Okay, so that's just kind of an intro to what I'll be doing. And now I'm going to just spend some time talking about Legendrians, Lagrangians, and what I mean by Lagrangian Cobordisms, and how you can use generating families to study them. Okay, good. Pause for a second, make sure there's no questions. I mean, I will make a lot more of this precise, but. Okay, so the contact manifold that I'll be working in is just Euclidean space. So I can think of R3 for today, but it will work in general for odd dimensional contact manifolds. So again, I'm interested in Legendrians, which are just n-dimensional submanifolds here, or just think of a one-dimensional submanifold if you're thinking of R3. That's always tangent to these contact planes. So this is our standard picture. This would be my Legendrian unknot here. So again, I'm just drawing the XZ projection. I add the Y coordinate of the slope. And in our contact manifold, we have this important Rabe vector field, canonically associated to it. And for our Legendrian knots, what we're interested in are the Rabe chords. So just trajectories of the Rabe vector field that begin and end on the knot. And this is where we're getting a lot of the rigidity and the invariance that we construct for our Legendrian submanifolds from these Rabe chords. Again, they themselves, you can shrink or stretch the lengths, and the number can change, but there's ways to calculate, define invariance using these Rabe chords. And here's just a picture just to remind you that I'm dealing today with usually in R3, but you could work in, for example, R5. This would be a Legendrian sphere inside R5, same thing. So I'm always working in R3. So I'm going back and forth between the contact world and the symplectic world. So I'm going to start with my contact manifold. I'm just going to cross it with R to get a symplectic manifold. Here's the standard symplectic form, d e to the s alpha. And in this symplectic world, I'm interested in the Lagrangians. So I'm just going to, that's just the natural condition here. We want the symplectic form to vanish on the Lagrangian. So to me, it's always so interesting, like Legendrians are so plentiful, they're so easy to make, but Lagrangians are really more mysterious. In particular, we're looking at exact Lagrangians, which are often interesting. So we want this, so this one form should not only be a closed one form, but we want it to be an exact one form. And Gromov tells us that there's no closed exact Lagrangians. But if I start off with a Legendrian here, here's a nice interplay between the Legendrians and the Lagrangians. If I start off with a Legendrian in one of these slices here, then I just cross it with R, and that will be an exact Lagrangian. So here's my picture that I tend to think of for Lagrangian Cobordism. So again, my slices can naturally be thought of as contact manifolds here. And so in the slice, I'll think of a Legendrian submanifolds inside two slices, S minus and S plus. L is always going to be exact, Lagrangian, and cylindrical. So between these slices, it's going to be compact, and then it's just going to be a cylinder over those ends. It's technical. Today I'll always be working with ones that are orientable, Maslow's zero, embedded, and immersed, or immersed. So when I work with the generating family, that's going to impose that it's already exact and Maslow's zero. And these sorts of Lagrangian cobordisms, there's also a different sort of Lagrangian cobordism, initially by Arnold, and Octave does a lot of this, but we look at a Lagrangian cobordism between Lagrangians, but again, this is the one between Legendrians, and this came up more in the relative symplectic field theory. Okay. And Lagrangian fillings are just where I'm just filled. You can think of it as a cobordism to the empty set, or you can think of it as a cobordism to a Legendrian unknot, one basic one here. And again, today I'm really always going to be focused on when they have generating families. And I'll explain a little bit more what that means in this setting. So I'm approaching this, through the generating family technique, generating families of functions technique. So just important today, I'm always restricting to Legendrians that can be generated by a function. If you're used to the holomorphic world, holomorphic curve world, this probably corresponds to Legendrians whose DGA admits an augmentation. And I'm interested in Lagrangian fillings that can be generated by, I'll think of this as an extension of the generating family for the Legendrian, the extension F of this function. And again, in the holomorphic world, this is probably corresponding to fillings that induce a specific augmentation. So I'll be fixing a generating family, trying to extend it. In the holomorphic world, would be the comparable problem would be to fix an augmentation for the Legendrians and look at all sort of fillings that induce that augmentation. Good. Okay. So generating families, a very classic technique, but was modernized, maybe a lot of great breakthroughs around 30 or so years ago, Ludenbach, Sikharov, Chacron, Vitrubeau. So I'm going to use these generating families. They've been used to study lots of problems, lots and lots of problems. So from capacities and camels and non-squeezing and symplectic homology and invariance. But today I'm applying them to study the geography problem. So I want to study these fillings by generating families. So the point is that I'm going to describe the Legendrian as a function, basically as the one jet of a function. And then I want the Lagrangian to also be described by a function, by the derivative of a function. But the whole key is that instead of these submanifolds, which are messy, I'm just going to associate to them functions. And the idea is, well, we have a lot of techniques to apply to functions, a lot of calculus. And so I'm just going to apply analysis and more theoretic arguments to these functions to get invariance of the submanifolds and relationships between the Lagrangian and Legendrian submanifolds. So this is just kind of outlining the general philosophy. In case you've never seen a generating family, here's a nice example to keep in mind. So again, I'm interested in this Legendrian. So here's a Legendrian trefoil. I want to describe it by a function. So I want to encode it by a function. So kind of like surf theory, sort of ideas. I'm going to construct a one parameter family of functions here. So starting like way back on this line here, there's like nothing above that. So I would think of just maybe a linear function. And then as I move along my real line here, my family, all of a sudden, something happens that cusp. So in my linear function, I want to introduce a pair of critical points. And the critical values of these points should correspond exactly to the heights in my front here. And so you can start to imagine, I go from a linear, and now I have like a cubic, and those heights grow. Oops, here I have another. I'm introducing more points. And then you just, this front, just think of the front just showing what's happening. Oops, I have some critical crossings. That blue and that green points are just crossing their critical values. And then as we go along, so this is just a way to describe a Legendrian by a sequence of functions, one parameter family of functions. So this is just the PDE that just describes what I was just describing here. So again, we're looking at the fiber critical points here. So the E is kind of like your extra variable here. So in this new gray direction. And then I just look at the one jet. So those equations. So here I just needed one extra variable. In general, as your Legendrians get more complicated, you'll need higher dimension here, but we're always in finite dimension, so that's nice. In practice, we don't really take a Legendrian and do this construction. That was just to give you an idea if you've never seen it. But a nice existence we have is from combinatorial rulings. So for Legendrian knots, you know that exists a linear at infinity generating family if and only if there's this graded normal ruling. So Chicano-Pushkar, Fuchs-Rutherford. I learned it most from Fuchs-Rutherford, but so rulings are just basically we chop up the front or the Legendrian projection here, the front projection, into these eye shapes. I kind of think of it. So here, I'm not sure the colors are showing very good, but here's like kind of a green eye, here's a red eye, here's blue eye, green eye. So we just kind of break at certain crossings. And there's some rules of when you can break and when you can't. But here's an example. This is a graded normal ruling of two different M52s. So whenever you have this, there's a way to canonically identify a generating family to each of these rulings. So both of these will have rulings, generating families. Here's one of the 7-4. So again, as I mentioned, I'll be looking at the M52 and the 7-4 a lot today. So here's a ruling for the 7-4. Okay, so once you have this function, so again, this ruling is just telling me there's a function that describes it. Let's think of what you can do with that function. So once I have this function associated to my Legendrian, well, then there's always like this little, cookbook stuff to try to figure out what you can do with the function to get something interesting. So I just call this difference function. So I'm just going to do 2 copies of that fiber. The whole key is you want to do something so that so it's interesting in the Morse theoretic sense. So I want the critical points to be interesting. So for example, if I do this difference function, then I'm recording the rave chords, and I'm recording at positive values, I'm getting one-to-one correspondence for the rave chords. And with 0 value, I'm getting actually a submanifold diffeomorphic to that submanifold, my Legendrian itself. So that's interesting. So that from there, now we just do sort of more theoretic ideas. I'm going to chop at epsilon, so I'm not actually seeing the submanifold diffeomorphic to lambda, but I'm just recording the rave chords. So here between this epsilon and infinity, so these are relative cohomology groups, I have a complex that's recording all those rave chords, and just normal Morse theory is allowing me to define homology, so gradient flow trajectories there. Okay. And from that, what I'll usually be talking about are these polynomials. So I'm just recording the dimensions of those cohomology groups. So again, what you really want to think of is the Legendrian, it'll have a generating family, and then I'm going to this polynomial. So that's usually I'm just Legendrian, generating family to this polynomial. So let's look at a couple examples. So here's, these are my M52s on my top line here. One of them has polynomial t plus 2. One of them has t plus t squared plus t to the minus 2. So we do have negative exponents. There's a shifting in the indices. So in general, you will have these negative exponents. Here's another t plus 2. So in general, I've written them this way. So they always satisfy this beautiful sort of symmetry. So in the Legendrian knot case, you'll always have this t. This is what we call Sobolev duality. There'll always be a t. And then there'll be a symmetry between t to the I and t to the minus I. So this 2 is a t to the 0 plus t to the minus 0. But in general, we'll always see like a nice pattern this way. And in fact, every polynomial that satisfies the duality, Sobolev's duality, can be realized by a Legendrian. So that was proved by Bourgeois, Sobolev, and myself. Okay, so again, Legendrians, generating families, polynomials. And again, these will correspond to, if you're used to the homomorphic curve world, these are corresponding to the Legendrian contact homology polynomials. You can also do this in higher dimensions. So I'll just mention it. It's really, really beautiful, some of the symmetry that you have here. So now you'll have, before, for the Legendrian knot case, we only had, let me go back one more. We only had a t power. But for higher dimensional manifolds, these are sort of your fundamental classes here. And there's a pattern here between, those have to sum up to the homology there. And then you have these other things happening, other terms. Let me just do some simple examples. For Legendrian S2, this corresponds to a T2. And now you have these other terms coming in here. Or if you do a Legendrian S3, this is what the duality says in this case. And every polynomial that satisfies this duality can be realized. So, okay, so the main thing that so again, we want our Legendrians to have a generating family. And the main thing we're pulling off of that generating family are these homology groups or these polynomials, just recorded by these polynomials. Now, I also want my fillings to have a generating family. So remember, these Lagrangians are living in the symplectization, but in fact, that's equivalent to a cotangent space. Okay. And I'm just gonna say a little more briefly here. So whenever I talk about a Lagrangian filling having a generating family, I really mean that Lagrangian that's living inside this cotangent bundle will have a generating family. And here's just the equation, PDEs that have to be satisfied by that F. So I want my generating family for the Legendrian and my generating family for the filling to be compatible. I want them, in some sense, you want to think of it like an extension problem. So there'll be a generating family for my Legendrian at the top. And I want it to sort of, I'll say, extends to the generating family for the filling, which will just mean this sort of condition. So kind of like becomes T of F. And again, that's because when we go to the symplectization, there's this sort of conical end that you end up getting. Okay, so that's just a little flavor for how you, for the Legendrians, the Lagrangians, the Cobordisms, and how we're applying the generating families to them. Okay, so now I'm going to describe how you can use these generating families to get obstructions to Lagrangian fillings, to talk about the geography. How do you apply it to the geography question? So one way to think of this first, without even the full geography, just kind of understanding what sort of embedded fillings you can have, goes back to like a Seidel isomorphism. So this is a generating family version of the Seidel isomorphism that Josh Sabloff and I proved a number of years ago, which tells you there's a lot of rigidity in embedded fillings. So if I have a Legendrian with a generating family, then the polynomial that's determined by the generating family is determining the topology of the filling. So and this left side, again, is a Legendrian invariant. So that's like what's information on the Legendrian boundary. The right side, this is just normal singular cohomology here. So this is just topology on this side. So one way to think of this in terms of the filling question is that if it admits a generating family compatible Lagrangian filling, an embedded one, it has to have polynomial, which just looks like that, t plus a constant, 2 times c naught. And that c naught, if it does, in fact, so if it doesn't, here's an obstruction here, so it has to have this polynomial, t plus 2 c naught, and that c naught is actually telling you what the genus must be. So different from the smooth world where you can just kind of add genus, the Lagrangians like to minimize genus, so you're not allowed to add it on. So I always think of this as just a real scarcity of embedded fillings. So in these polynomials, this one potentially has an embedded filling, this one potentially has an embedded filling, this one does not, okay, no embedded filling. And I'm just repeating something that I said earlier. All the polynomials have this form and all these polynomials can be realized. So in some sense, most Legendrians really don't admit, so only the Legendrians of this form have a chance of admitting an embedded filling. So even though, the embedded fillings are very scarce, very rare, but any Legendrian that admits it has a generating family will have an immersed GF compatible filling. And going back to work that I did with Bourgeois and Sabloff. And so now the question becomes, that polynomial tells us a lot about the embedded ones. And now the question is, well, what does this polynomial tell us about the embedded and the immersed ones? What does it tell us about this Lagrangian geography problem? So now I'm entering into the results that Pesamenti and myself did. Okay, so let's just start with say you have a Legendrian knot that has a generating family polynomial. Okay, so again, I went through this whole procedure to some way from the Legendrian. Once you associate the generating family, you get this homology groups and you record this polynomial. So this polynomial tells you that if you have genus 0, so you're just looking at these disk fillings, if I sum up all that CI, that's going to be a lower bound for the number of double points. Okay. And if you want to have other genus, well, there's some swapping that's allowed between the genus and the index 0, or sorry, yeah, index, well, I'll say index 0, these C0 points here, double points. And that there's also this mod 2 relationship between the genus and the number of double points. So this is really pretty cool because it's telling you the polynomial has a lot of information encoded into it about the geography problem. So let me just, now I'm going to go back to some of these lattice pictures. So now we're going to get what we call checkmark geography answers. So if my polynomial looks like this, again, this is like a t+2 polynomial. Okay, so here you could, that was a form where it could have an embedded filling, or it could have a disk filling with one double point. And again, in this blue shaded region, it's not all points, but it's this mod 2 relationship. So here I'm kind of where the sum is odd here. Here are some different pictures. Here, C0 vanishes, and this is a polynomial. I'm just writing the coefficients that are C0 vanishes, so my check mark kind of degenerates into a line here. And here you can see where the non-ones sum up to be an even number, so I'm kind of getting the even lattice in here, so all the even points. And this, again, the C0 is kind of like the depth of the check mark that you have. So these, again, just potential. It doesn't say anything about that these can be realized, but just potential. And if I really wanted to, I just kind of said sort of the corollary first before the theorem. So if you wanted to formulate a immersed GF-Isomorphism, kind of an immersed version of the Seidel Isomorphism, what we do is from an immersed Lagrangian filling, say it's the, from the immersed Lagrangian filling L, I form this complex where this complex C records the topology of the domain of the immersion, so before it becomes immersed, and the number and indices of double points. And then we define that there's a homology groups of this immersed filling. And actually what we have here is there's this, the Seidel isomorphism sort of becomes the generating family cohomology groups here are recording this homology of this immersed filling. So that might be a little mysterious. So I'm just going to explain a little bit where in the proof here. So you get unobstructed in the sense of flare theory. Okay, Octav was writing a question. Octav, can you explain your question a little bit more? I'm not quite sure.
So yeah, it's maybe not a good question, but I was just curious if these feelings you get, they are immersed, but immersed Lagrangians also have floor theory, because, you know, floor theory depends on some obstruction, but sometimes this obstruction is vanishing, or it can be annihilated by some choices of maybe marked intersection points, or any case. So if you can, generally, if you can define homology like you do, we expect it to also be possible to be defined in terms of floor homology with some variant of it maybe. So I was curious if you already know the answer to this, or
I don't know the answer. I would expect that you could do. Yeah, Lenny says yes. I would expect you could do it. Yeah, with homology. Yeah, good. Thanks, Lenny. Okay. Oh, Hiro Tanaka. Okay, if you have time for this. I see. if you have time. Yeah, so I'm usually using real coefficients, positive characteristics. Okay, for this higher dimensionalized. Yeah, so I'm usually using our, real coefficients. I should have said that, yeah. Okay, so let me just give you a little flavor for how you construct this. So again, I have a generating family for the Lagrangian that is sort of compatible with the generating family at the top. So again, the whole game is you start with this function and you want to do something with it so its critical points are interesting. So from a function, I do this sort of, you want to think about a perturbation or shearing. The point is that when I make this big delta function, the critical points are interesting. So I'll have a critical submanifold that looks like the domain of my Lagrangian before I immersed it. It's also going to, for every double point in the image of, under that immersion, I'm going to get a pair of critical points. And you can say something about they're going to have opposite critical values, positive, negative, and you can say something about their indices. And then that's kind of in the Lagrangian. So I'm recording the topology of the domain of the Lagrangian and the double points of the Lagrangian. And I'm also getting critical points for each Rabe chord. So something interesting about the Legendrian boundary. So this is kind of how I would think of this. It should work for any field. Yeah, it should work for, okay, Claudio, so it should work for any field, yes. Okay, so here, so here's how I would think of. So in this picture, I would see, oh, here we have a Legendrian that has 3 Rabe chords. So that's what those 3 dots are representing. And the filling would be genus 1, and it has 2 immersion points, 2 double points. So the point is here is we kind of look at these the sublevel sets at appropriate levels. And then by the compatibility, you can associate this part, you can think of this as a cone or a relative cone of these spaces. And then standard sort of algebraic topology arguments gives you a long exact sequence here. And then from that long exact sequence, you can show that these terms, that every third term will vanish, which is exactly giving you your isomorphism. So that's why you're really seeing the boundary here recording where we're getting terms here, recording the topology here, the topology of the domain and the double points. Okay, I know that's kind of a little fast, but I just wanted to give you a flavor of some of the Morse theory arguments. This is kind of how I actually do this and think about this. So this is kind of the game we play. So say I have a polynomial which looks like t plus 2. So this is kind of how I draw my charts. Okay, so I draw my charts T2, T's decreasing this way. It's just because of the shift in index here. So basically, I want to have 2 T0s and 1 T1. And so by the homology, so I have to record that either from the topology of the domain or from double points. So you can see, oh, if I have T plus 2, yeah, I can get an embedded genus 1. So again, H0 is corresponding, that's again sort of like your fundamental class. That's why you're always seeing T1. You're always seeing some H0 of your surface and genus 1 here. Or I could, for example, how else could I do it? I could also get this like T plus 2 from a disk. So I only have H0, no H1 anymore, and 1 double point of index 0. Or I could have both. I could have H0, I could have genus, but now if I have genus, I have to have more double points, right? So now I could have 2 double points, kind of with, these are just representing some potential canceling. Or I could have genus 2 with 1 double point, so here. So this is just kind of the idea. We can start to get a flavor for why we're getting some of those check mark shapes. But you could see also, if I just tried to do this with a disk with 2 double points, at least into, you know, just play around with, it cannot be recovering this t+2 with those sorts of, that sort of configuration. Okay, not completely rigorous, but hopefully that's how we play around with. Okay, so here's the potential checkmark geography, and going back to some of these, that's how we were getting this, again, from the, again, the parity and the shapes. And now the question is, again, this is just potential, again, just to emphasize, this is just from the polynomial. This is just the algebraic from the polynomial. You can realize now the natural question is, which of these can be realized? Okay, so now entering the last part of the talk, just talk about constructions. So the embedded moves are fairly well known. So at least some moves that we have. So basically, we know if our Legendrians are isotopic, then you'll have a GF compatible cobordism between them. So this will just be a concordance. But in general, you could do these pinch moves, again, with in the framework of generating families. You can also fill a basic knot here. So again, these are kind of the basic moves, these pinch, isotopy pinch, and these saddle move, and the filling moves here. So these are kind of fun. So here you can actually see an embedded filling of 7-4. So here's my 7-4, so just the green and the blue here. I started with a ruling, because the idea is, okay, I start with the generating family. I'm just encoding the generating family by this ruling. So the red lines are just, I'm going to pinch there. So here I pinched it. And then well, now I'm pretty good. So now I'm just going to do some Reitermeister moves, make it smaller. There, there, and there's the unknot. So that's kind of like a movie for the embedded filling, a genus 1 embedded filling of 7-4. You can also do some immersed moves. So for example, if you have a ruling that's well behaved with respect to a clasp, okay, so here either I'm going to unclasp these 2 strands. So either the rulings break at both crossings or they don't break at all, so you don't switch at all at either of these crossings. And then, so as long as you do this unclasping, so then you'll have an immersed compatible cobordism with a double point, and I actually know what the index of the double point is. There's like a Maslov index as you're going around here. There's also a clasping move, but this is going to be the main one for the move, the clasping move. Okay, unclasping. Okay, here's another movie for Joe. So here, so here's an immersed disk filling of 7-4 with 3 double points. Okay, so here I'm starting. I just highlighted these 2 areas. That's where I'm going to unclasp. So there we go. So unclasp it, just left the little circles there. Let's just straighten that out. Okay, good. So I've done 2 double points, and now I'm going to focus on this region here. There we go. So there's another region where I can unclasp. Again, it's well behaved. So I unclasp it. And now we're just going to do some Reitermeister moves. So again, move it, get rid of it. And now I'm at my unknot, which I know I can just fill. Okay, so this is, so what can we say? So now let's see, tying the 2 parts of the talk together. So from a polynomial, I have this sort of region here. Again, just potentially, I don't know which of these can be realized. So here, I just realized that I could do this. This was, again, the embedded one, the genus 1, embedded with genus 1. Or I could do the immersed with 3 double points. And in this Lagrangian world, you can always fix the genus and go up by 2. Okay, so here I can go north by steps of 2, or I can also go northeast can increase the genus and increase the number of double points by 1. So this tells me that I can realize this whole blue. Just from those two, I know I can realize everything in that blue shaded. Again, the mod 2 relationship. So here's a little way of seeing some, like adding 2 double points. So I have this Lagrangian filling, but you can think of lifting that Lagrangian, that 2-dimensional Lagrangian, to a 2-dimensional Legendrian in 5-dimensional space. And here's sort of a surgery. You can do the surgery on these Legendrians. The rave chords here are, of course, in the Legendrian are corresponding to immersion double points in here. So here, where it can add 2 double points. Again, whenever I see these rave chords, these correspond to double points. Or you can see adding genus and a double point. So I'm adding a handle here. The handle will necessarily have a double point and a rave chord, which corresponds to a double point. Okay, so here it's a smooth versus Lagrangian 7-4. So again, here's the smooth geography using Owen Stirl's sort of results here. And here's the Lagrangian geography. So this is, again, the best I'm getting. You would, over here, I could, in the smooth world, you could realize a disk with 2 double points. I can't in the Lagrangian world because, again, I have this mod in my generating family, at least, filling world, and I can't realize it there. I have that mod. So this is the best I could do, and I can realize everything there. M52, you can do a similar procedure for like M52. So here again is the smooth geography. Here's the Lagrangian geography here. And again, this is for this particular generating family. I mean, when I have to start, I'm always fixing the Legendrian. On this side of the picture, on the Lagrangian part, I'm always fixing a generating family and looking at its associated fillings, compatible fillings. Here's another M52, again, diff one that's not Legendrian isotopic to it. Again, here you really see, wow, that's really different from the smooth world. So for the remaining time, I'm just going to, Octav, can you measure the size of the fillings? Okay, Octav, did you want to explain your question? Like the spectral type invariant for the generating? You mean like the indices or the size of the filling?
No, the values. So what I was thinking is that, you know, in all this sort of machineries that we do, traditionally we used to compute homology.
Yeah. And
then we can also look at the actions, you know, in floor theory, like the action functional. And then this gives you some ways of measuring the size of objects that appear. So here you have Lagrangian fillings, but you know, whether you use floor homology or whether you use generating functions, you have some actions. So you could in principle measure not only the genus and the number of double points, but also kind of the size of the Lagrangian. And so in fact, I think you can get really geography there, in the sense that, you know, geography requires some sort of distance between and I think so I was just curious if you looked into that, because you had this other work, you know, about the size of Lagrangian Cobordism, right?
Right.
Legendrians. So
yeah, I haven't thought about that, but that's a good question to think about. Yeah, no, thank you. Yeah. Good. Yeah, so the rest of my time is just going to just mention some other questions. So I kind of chosen ones that I kind of know a lot of information about with this M52 and M74s, but in general, what I'm really interested is, when can you not realize the chart determined by smooth topology and the polynomial? So, I mean, we're kind of, so, are there deeper obstructions? I'm just using sort of like the vector space structure here instead of like the product relations that you have on these homologies and A infinity relations. So, for example, like there's a result partially in from the holomorphic curve side. So, ECU applying results of Ekholm and Lekili, they showed that there exists a Legendrian and an augmentation, so that the polynomial looks like t plus 6. So for me, that looks like, okay, so it potentially has an embedded genus 3 filling of it, but then they show using the A infinity structure that it cannot have an embedded filling inducing that augmentation. So there, that's kind of answering a geography question on that side. So like seeing these obstructions and there are ways, the generating families, there are ways to form products. So Ziva Meyer has done this with, so can this, from Ziva. Okay, so Denny was asking if ECU's example admit a generating family. It's a really complicated, I haven't tried. I would, yes, it will admit it. It has an augmentation, so it will admit a generating family, but I haven't actually played with it too much. So yeah. Yeah, so I think a lot of this, like really understanding, more obstructions in the table really involves kind of deeply understanding some of the relations in this, on these groups. Yeah. Oh yeah. Okay, there's another good question. Are there similar obstructions via generating for exact Lagrangian caps? I don't know. Usually the caps are only coming from stabilized things, and so there we don't really have. It would be interesting. I wouldn't know how to do it for a cap. So there was a question from Philip to everyone. Yeah, so that would be an interesting question. Are there similar obstructions for exact Lagrangian caps? That would be really good. Yeah, I don't know of any right now where you could do that. So lots of there, but the caps are interesting also. So kind of related to the geography question, there's like a mutation, what I kind of think of as a mutation question, how are they related? So even in the smooth world, these are all kind of vague questions, but in the smooth world, for example, I know I can always move southeast in here, in this direction. In the symplectic world, you can't always move southeast on your diagrams, but this is work that I've been doing with Ursula Capovella-Searle and Noémie Lecout and Malise Limon-Zino and Emmy Murphy and UPenn. Just exploring how double points with particular indices and actions, which we call VIA, can be traded for genus. So you can move in this direction if you're working with, certain types of double points. So in our world, we're kind of looking at different sort of geography where TB is determining a line. And here the question that we've been looking at is, can you always go backwards? Can you kind of trade genus for double points? Again, sort of this sort of geography question. And I'm not talking about this today, but I think UPenn, I think, is talking this afternoon. She may be mentioning some of these results. So, and in general, you can't in general, but again, this is kind of deep using augmentations and A infinity arguments to prove this. So in going back to my checkmark world, how this fits in general, I'm not able, I just know I can't in general go to the, could go in that direction, but it's really on this edge of the check mark where that's where the interesting things happen, you know, because again, once I can always go northeast, so can, you know, the southwest, northeast, southeast, northwest sort of direction here. But that's where you have the double points with the right indices at least. Not really sure always actions and things, but again, just some brainstorming, lots of interesting questions with this geography. Yeah, so can I interchange there, understanding when I can or when I can't. And then there's this kind of a little bit more tangent to what I've been, but I think that's really also very interesting, like how many options are there? So once you fix the topology and the number of immersion points, and just some related results, you know, so Echolm, Honda, Kalman, Pan, Cheney, Truman, so Williams and Zaslow. So there's been a lot of study about the number of fillings of torus knots. So for the max TB 2n torus links, you get a Catalan's number of embedded fillings. Again, they're smoothly isotopic, but not pairwise exact Lagrangian isotopic. And then even more recently, Castles and Gao have proved that most max TB torus knots admit infinitely many embedded Lagrangian fillings that are smoothly isotopic, but not Hamiltonian isotopic. But again, that's a little different than, I mean, really interesting. I don't know, like if I tried, I've been kind of like, I'm fixing some boundary data. So here in these problems, they're not fixing any boundary data, right? You know, in fact, they're often showing that they're different by detecting things about the boundary. I don't know if you've kind of fixed boundary data. Can you count the number of fillings with a fixed topology and double points? So lots of different questions. I really have no idea how to do that, but good. Okay, so thank you. That's
Thank you very much. So let's